Hi, my name is Patrick, and I'm going to talk about our paper Risk-Aware Linear Bandits with Convex Loss. To put things in perspective, let's first recall what a linear bandit is. A linear bandit is a sequential game where at each round, a player observes a set of d-dimensional vectors, called the action set, and selects one of them. We say the player plays the action xt, and in return, the player receives a reward yt. And this reward is distributed according to a statistical model. A statistical model is simply a collection of probability distribution indexed by a parameter phi, and the link between the action played and reward is done through this parameter. We assume this parameter is linearly described by the vector xt. That is, there exists a vector theta star unknown to the player that generates this parameter phi. And the goal of the player is to minimize the regret. That is, the cumulative sum of the difference between the best possible action and the action that we played. And the quality of the reward linked to an action is evaluated through the expectation. Now, typically we make an extra assumption in linear bandits, that is, the parameter phi actually describes the expectation of the statistical model. And so this regret simply becomes the cumulative sum of the maximum of the linear form over the action set minus the linear form evaluated at the played action xt. An example where this happens is simply a Gaussian model with fixed variance, say 1, and phi just is a free parameter that describes the mean of the distributions. In this paper, we're interested in generalizing this to different measures than expectation. So what we call a risk measure here is simply a mapping from probability distribution to a scalar value, the same way an expectation summarizes a whole distributions into a single number, and we want to minimize regret that is expressed using these risk measures. So to give you an idea of why we're interested in doing that, let's consider an example from agriculture. Think about two farms. One is the green farm and the other is the blue farm. And they are located next to each other, so they have the same weather conditions, but they only differ in their crop management policies. So for example, they use different sorts of fertilizers. What you see here is the distribution of crop yield for each of those farms. And this is a distribution because if you assume the weather is stochastic, the crop yield you get when you harvest is a random variable. So you see here that the blue farm is much more aggressive in its management. It can get very high yield, but at the same time, it can get very low yield quite frequently, and even zero yield. That means the harvest is completely wasted. On the other hand, the green farm is much more conservative in its approach. It doesn't get as high yield as the blue one, but it doesn't get as low yield either. It's much more concentrated. So if you look at the mean crop yield, the blue farm appears to be slightly ahead because those very high yield, they tend to distort the mean quite a lot. But if you look at a different risk measure, for example, one that is called the 5% expectile, the green farm appears to be ahead. And what this expectile measure does, it's actually a generalization of the mean, but it highlights differently the left tail and the right tail. In this case, it puts much more emphasis on the left tail. So basically what we are trying to do in this paper is to do these sort of things in a sequential setting using linear bandits. So to be a bit more precise, the sorts of risk measures we consider are called elicitable risk measures. And an elicitable risk measure is simply one that can be written as the minimum over some free parameter xi of expectation of a loss function that is convex, and that takes as arguments the reward variable and the parameter xi. Moreover, we say that such a loss is adapted to the bandit if the corresponding risk measure is linear on the statistical model. What that means is if you take the risk measure of the distribution p phi, what you get is just phi. So it's exactly the same setting as in the classical mean linear bandit, where we had the expectation instead of rho, and the phi just described the expectation, the mean of the distribution. So if we assume that the regret of the bandit using the risk measure has exactly the same form as in the classical mean linear problem, but this time the linear form in xt, it doesn't describe the expectation, it describes, for instance, the expectile. So we can try to optimize the expectile in a sequential setting. Examples of elicitable risk measure, there are plenty of them, but the most commonly used are the mean. So we can make sure that in all we say, we fall back to the standard classical bandit if we take this risk measure. The p expectile, which is defined using this formula. Another one that is quite popular is the entropic risk, which is defined in this way. And there are many more, but an important point is that the variance and the CVaR are not elicitable risk measures. At least they are not what is called first order elicitable risk measures. So for now, they're outside the scope of this work, but they may fit within it again in later work. The main algorithm we introduced is called lean-UCB-CR for convex risk. And it's exactly the same algorithm as the classical lean-UCB, except for one line, which is the one highlighted here. Basically, we replaced sequential ridge regression by sequential empirical risk minimization. And by risk, we use the loss associated to the risk measure we considered. Apart from that, it's exactly the same as lean-UCB. In particular, it's an optimism-based algorithm. So that means it is greedy with respect to the current point estimate of the parameter, corrected by some exploration bonus. And the whole purpose of the analysis is to design a correct exploration bonus that makes sure the regret is sublinear. An important point, an important difference compared to lean-UCB is that this problem doesn't have a closed form solution. So we have to numerically solve the minimization problem. Hopefully it's convex because L is convex, so it shouldn't be too hard. The analysis relied on a quite important assumption, which is that the curvature of the loss is bounded, both below and above. To understand a bit more what it means, we considered two sorts of Hessian matrices in this problem. The first one is the global Hessian, which is same matrix as that's ubiquitous in the analysis of lean-UCB. And we also considered what we call the local Hessian. So it's the same matrix, but each element of the sum is weighted by the Hessian of the loss. And we say it's local because it actually depends through this weight on the parameter theta. So, for example, if you're at time step t in your algorithm, here you can replace theta by your point estimate of theta at time t. Now this has two consequences. First, if we try to mirror the standard proof of lean-UCB, we want to have some self-normalized time uniform concentration. But and we managed to make one, but the difference with lean-UCB is that it's normalized not by the global Hessian, but by the local Hessian. That makes appear this parameter here. Another difference is that in the standard UCB case, this sum is simply the sum of the centered errors of the model, which is a martingale. In our case, we have to consider this more complicated expression to retain the martingale properties. Apart from that, it essentially works the same as lean-UCB, and you can extract very good time uniform confidence sets for the true parameter using this equation. A second point is that in the proof that optimism works in lean-UCB, it's sort of hidden, but there is a geometric argument. Because basically you need to compare the geometry around theta star, the true parameter, and the geometry around theta bar, the point estimate at time t. And in the standard mean linear case, because the geometry, the natural geometry to use is the geometry induced by the global Hessian, the geometry is the same between the 2 points, because it's a global Hessian. In our case, the natural geometry to use is the local Hessian, that depends on the point estimate. So we need to have a way to transport the metric induced by the Hessian from one point to the other. That's a bit technical, it's done in the paper, but that introduces some more complexity. The main result of this paper is a regret bound for the lean UCB CR that is essentially the same regret bound as lean UCB. In particular, it scales as square root of time horizon up to some logarithmic term. It depends linearly on a term that is essentially the standard deviation of this term here. That comes from the time uniform self-normalized concentration bound we have. And an extra term we call kappa, which comes from the transportation of Hessian metric. Now in our case, because we made the assumption that loss was bounded from below and above, we showed that kappa can actually be just the ratio of the upper bound to the lower bound. But actually, we conjecture that kappa in some cases could be made constant, irrespective of those lower bound and upper bound. That's why we separate kappa from just this dependency here on square root of m. The reason why we conjecture that is because of recent advances in logistic bandits, which is quite similar but not exactly the same sort of setting. Kappa was found to be just related to the intrinsic property of the logistic function. So we hope that in some cases, if you make some more precise assumption on the loss, you can have a constant kappa that you can just basically forget about. Now, the one thing that remains is that we have to solve this convex problem at each round. And that can be quite costly because we do not have a closed form expression. So instead, we introduced a variant of the lean UCB CR algorithm that does not solve this problem, but instead updates the parameter theta hat using an online gradient descent. To be more precise, we use an episodic online gradient descent. And by that, we mean that we only update the parameter after h step. And we update it using the full batch of size h of the previous observations. And we showed in the paper that essentially this does not modify the regret. The regret still scales as square root of t plus some polylog terms in t, and essentially similar coefficients in front of it, as long as the batch size is large enough. And large enough, we have an explicit expression, but basically it scales as d to the power 2, the dimension of the actions. To finish, we ran some numerical experiments. So here we have a bandit with 2 arms, and similarly to the examples from agriculture with the 2 farms, we designed the 2 arms so that one is best using the mean criterion, but is the worst using the expectile criterion. So in blue, we have the standard lean UCB model that correctly identifies the arm with the best mean reward, but that's also the worst expectile, so the expectile regret grows linearly. Here the scale is logarithmic, but the regret actually grows linearly. And if you run the risk-aware version, the expectile lean UCB, you see that the regret flattens out, and the arm with the best expectile distribution is actually identified. The relaxation using OGD is somewhere in the middle. It flattens out, but it starts from a higher regret because of the extra exploration induced by the noise of the OGD updates. But it's also much, much faster than lean UCB CR. Now, thank you for listening, and if you want to have access to the full paper, here is the QR code. Thanks.